types of solids. We have amorphous, as shown here on the right, quite distorted, kind of crazy, chaotic. There's no real repeating pattern. It's indistinct, and hence why it's disordered. However, what we see here on the left side of this picture, this is a crystalline structure. It's a lot more ordered, more organized. It has a unit cell. It's distinct, and therefore it's a lot more organized. It's an ordered array. Next, all of these here belong under the crystalline. Let's have a look at the first one. For the metallic, electrons are not stuck in the bonds, which means they are freely moving. They're freely moving because the electrons can go from one ion to the next, no problem. So they're not confined in any directional bond. They're free to move around or wherever they wish, and hence why they are malleable as a trait. So all of these here are examples. Steel here, it's carbon and iron. Carbon is a nonmetal, but still acts as metallic. Next, we have molecular. It's when the electrons are stuck in the covalent bonds. Because they're confined within this bond segment, again, the electrons this time, unfortunately, are not able to be freely moving. So non-conductive, because the electrons cannot give the neighboring electrons the kinetic energy. Next, it doesn't take much energy to separate the molecules. So even weaker intermolecular forces can separate them. So all of these here are nonmetals because they're connected together in a molecular compound. Covalent, again, nonmetals only, however, like above, but this time it's a network that is oriented a little bit differently. In a covalent network, electrons are stuck in directional bonds, so they're non-conductive. However, some of them, like these, can be conductive. Because if we look at graphite, for example, here on the left side, if we have carbon and carbon, and let's say this double bond has a pi bond on this side and a sigma bond on this side, these pi bonds can carry delocalized electrons to go from one carbon to the next, providing a path for electrons to travel and hence maybe conduct heat, provided that there's enough sufficient charge and there is sufficient amount of pi bonds available. It is possible. Now, there is no distinct beginning or end, because whenever these bonds break, it's not the actual intramolecular bonds here that breaks. It's not there. What's actually breaking is the entire unit cell. So because the entire unit cell breaks, it's this whole macromolecule that's in play. Hence why it is very, very strong. There's no distinct beginning or end. We can't pinpoint where it's happening. It's the whole thing that breaks. So this whole big macromolecule makes it very strong and glued together. Last, we have ionic. It creates a crystal lattice. The lattice means it can't move. So if we have a positively charged ion and negative, and you put them together, it is an ionic compound. Pi bonds are oriented top to bottom because they have sideways crossovers only.